Okay, so today, guys, we are going to continue in chapter 9, and David, I'm going to get you that. I just haven't got your email, but I'll send you that link here later this morning for what we did yesterday, so you can see that. But we're just going to continue chapter 9. Monday, no Google Meet. We're still remote the next 2 weeks, is my understanding, at least the next 2 weeks. Hopefully after that you'll be back. But who knows? I don't know the plan. But so no Google Meet, but I will post a lesson. We'll continue in chat. Hopefully by the time we Google Meet on Tuesday, we will real quick wrap up chapter 9 and we'll move into chapter 10. Your quizzes for chapters 8 and 9 will be due on Wednesday. And so on Tuesday during our Google Meet, if you have questions or if you want to Google Meet later on in the day, we can do that. So that is the plan. So Monday, no Google Meet. There will be a lesson posted, probably finishing 9, getting into maybe chapter 10. Tuesday, we'll Google Meet, kind of wrap up 9, move into 10, questions on the quiz. The quiz will be your next thing due. That'll be due Wednesday. It'll be kind of a normal week. We will not Google Meet on Monday and Wednesday, but there will be lessons posted. So the next thing due is your quiz, and your labs I'm working on grading right now. So I don't know if they'll be in the grade book today, but they should be early next week. So, okay, any questions you guys have? We good? And like I said, David, I'll get you that link maybe even after our class so you can see what we did yesterday. Okay, so where we left off, what we were talking about in chapter 9, we were talking about, really to me, explaining the dots. And I told you there's 2 theories. One of them, the one we're going to learn, is called the valence bond theory, which is also called the localized electron theory. And the other one we're not going to need to know, but again, if you take chemistry past our class, you will, called the molecular orbital theory. And this is where we left off. So here was our steps, okay? So the same steps. We did PF3, so here in a second I'm going to go back to the board. But we're going to do the dots. We're going to count the electron domains. All this is connected. This is the same thing I said in chapter 8. We're going to do the dots. We're going to count the electron domains. We can then determine the shape. We can determine the bond angle. We can tell if it's polar or nonpolar. And we can also explain the hybridization. So we're going to do the dot structures. We can come up with the shape, the bond angle, polarity, and then we can also talk about the hybrid orbitals. So I'm going to do here, we did PF3 yesterday. So I'm going to do the sulfide ion, SO3 -2, and then I'll do this NH2 negative. Okay, so let me come back here. Okay, so to the board. So if I go back and I do the dots, and we ought to be getting, you guys should be getting hopefully really good at doing dots now, because we've done a lot of them. Sulfur, 6 valence electrons, so I'm counting the valence electrons. Oxygen, 6 times 3 is 18, and then -2 means there's 2 more electrons, so 26 total dots. So then I put sulfur in the middle, and I connect everything around it. Again, the first element in the middle, the other elements around it, and then I fill everything's octet. Now I count, so I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Everything is good. So in this now, if I go back and I count so I did the dots, now I'm going to count the electron domains. So if I go back and I count the electron domains around sulfur, a non-bonded pair is 1, so there's 1, 2, 3, 4. So this is 4 electron domains. So this is a derivative. This is a derivative of the tetrahedral shape, the 4 electron domains. And so this is like ammonia. So the shape of this is pyramidal. And one thing we're going to do next week, I'm going to put it on. I'll put this on Tuesday. We're going to do the quote lab that I was hoping you guys were going to be here and do, but now you're not, was an advanced Tinker Toy lab. And so you're going to have to fill this out, and I'm going to kind of try and show you as best I can in 2 dimensions how you would show this. So this is is pyramidal. The bond angle is going to be a little less than 109.5. And so the way you would diagram that, if you could see the tetrahedral or the pyramidal, if you could actually hold it, this oxygen would come towards you and these two would go away. So how you would show that in 2 dimensions, if something's coming towards you, I always just shade it in really dark, like this. And then if something, and these two would be going away, I would show that as a dashed line. And again, I'm not going to hold you to this because you're not going to be able to actually build these molecules. I'm just going to try and show you the best that I can. Okay, and then the final thing is the hybridization. So remember, with 4 electron domains, so everything kind of goes in families by electron domain. So this would be sp3 hybridization. So and then the polarity and non-polarity, I forgot that. This shape is always going to be polar if the elements have a difference in electronegativity. They do here because of the oxygen. So this would be a polar molecule, so it would look like this. And the oxygen end, because it's so electronegative, would be the negative end. Okay, so let me go back. I've kind of been going back and forth here, so I'm going to move. I'll come back so you guys can see this if you need to. But just again, reviewing over here, and again, I was hoping you guys were going to be here so you guys could actually see this. But it probably will not when you guys come in because we'll be to chapter 10. Can you guys see this, Mason, Kara? So what we were doing was this one, AB3E, again, the 4 electron domain family. This is the pyramid, less than 109.5. It is polar. And David, and this is where you'll see this in the video that I made yesterday. They're grouped. Their hybridization, again, I explained this, and you'll see it, David, and everybody else, I think, was here yesterday, is sp3. So that's sp3 hybridization. Okay. And again, if there's something you can't see, if you have a question, if I'm going too fast, let me know. Okay, so that's sulfide ion. This is called amide, A-M-I-D-E, amide ion, and it's actually the strongest base that there is. There's the strong bases we kind of talked about, and if we get time, we'll talk more about this. But it's the alkali metal hydroxides, so LiOH. These are the strong bases, kind of not the point of this. This is, we're going to do the dots and the shapes and everything, but the strong bases, just for future references, are the alkali metals with hydroxides, so LiOH, NaOH, KOH, RbOH, so on, as well as 3 of the alkali metal hydroxides. So CaOH2, SrOH2, BaOH2. Well, this is the strongest base there is. Okay, but we're here to do the dots. So I've got nitrogen has 5 dots.
Sorry, I didn't quite catch that. Could you please repeat it?
My phone is talking to me. This is scary. Okay, so nitrogen has 5 dots. Hydrogen each has 1, so there's 2, and then the negative 1 needs 1 more. So I get 8 total dots. Okay, and then, so I put nitrogen in the middle, and remember, hydrogen only needs 2, and then I fill the octet, so it looks like this. Okay, so there's the dots. Now I count the electron domains. So there's 1, 2, 3, 4. So there's 4 electron domains. So this is in that same group. It's the tetrahedral group, but when there's 2 non-bonded pairs, the shape of this is bent. And the bond angle is less than 109.5. And again, probably, it might be, if we do come back the week of the February 8th, then that will probably be the week we'll have the test on chapters 8, 9, 10. I usually will put one on there. Could have applied to this one, but why is the bond angle less than 109.5? Is because these non-bonded pairs, they take up more space, so they kind of squish the angles. So, and this is how I would diagram that. Bent would truly be in 2 dimensions, would look like that. This would be polar. Bent is polar, and because nitrogen is one of those 4 elements, it's real electronegative. So we have a negative and a positive. Okay, and then the final thing, again, because there's 4 electron domains, this one is also sp3 hybridized. And they're not all sp3 hybridized. It depends on the electron domains. How many electron domains? If there's 2 electron domains, then it's sp hybridization. If there's 3 electron domains, it's sp2. If there's 4, it's sp3. And we're going to talk about 5 and 6 electron domains right now. Okay, we okay with that? Dots, shapes, bond angle, polar, nonpolar, and now hybridization. Okay, so now we're going to go into what was new stuff for us back in chapter 8, which was the trigonal bipyramidal and the octahedrals and the derivatives of those. So we're going to explain the hybridization of those. Okay, so I'm going to leave this up for a minute, but the third period, so this is explaining that expanded octet concept that we talked about in the last chapter. And this only occurs for the third period elements and below those. So third period elements have empty d orbitals, and that's why this will not occur for elements in the first row or the second row of the periodic table. It has to be the third row and below, which can accommodate hybridized orbitals. Molecules with a trigonal bipyramidal, the AB5, or any of those derivatives, their hybridization is sp3d. I'll try and explain that. And again, I'm going to try and explain this hybridization. I don't know how well I explain it, but I'm going to try and do that here. Okay, I'm going to minimize this. And again, if I'm going too fast, tell me. And I can put that back up here in a second. So so again, if I go back to my same processes, so BR5. So I'm going to do the same thing I was doing. I'm going to do the dots, count the electron domain. So phosphorus gets 5 valence electrons. Bromine, 7 times 5 is 35. So we get 40 total dots. So then I put phosphorus in the middle and the bromines around it. And then I fill the octets of the bromine. Okay, and now I count, so I've got 8, 16, 24, 32, 40, which is exactly what I want. Now I count the electron domains. There's 5. 1, 2, 3, 4, 5. So there's 5 electron domains. So this is good. This fits in that AB5, the trigonal bipyramidal shape. But now explaining the hybridization. So if we look at phosphorus, we know bromine ends as 4p5. This is the bromine. So bromine has in the 4p orbital, which is the last orbital, 4p5, so it's got a pair, and then a single. So it's going to form one bond. And again, what we're really explaining here are the dots. This is why bromine is like this. It's got that single dot, which is here. But phosphorus, this is that expanded octet thing. So phosphorus, again, it's electron configuration. So I'm going back to the electron configuration, the orbital diagram, 1s2, 2s2, 2p6, 3s2, 3p3. So if I look at just the outermost energy level, so here's the 3s. So the 3s2 is a pair, and then the 3p3 looks like this. And if you think about the dots for phosphorus, it looks like this. Again, sometimes I go too fast, but that makes sense. So there's a 3s2, the pair, and then there's 3 singles. But what happened here is that phosphorus now is expanded into another octet. And remember, this is why this only occurs for elements that are in the third row. So beginning with sodium and magnesium and across and below. Okay, it's not for hydrogen, helium, or lithium to neon, because those don't have available d orbitals. So they're just sitting here empty, these 3Ds. So here are the 3Ds. They're empty. So what happens here is that same thing we talked about yesterday, is one of these S's promotes, and then these all right here hybridize. They hybridize, which means they become equivalent. They're a cross between the S, the P, and the D. And so what this is called SP3, a single S, 3 P's, and a D. And so what you have then is you have this. To be honest with you, I don't even know the shape of these, but I've got the S, I've got the 3 P's, and then I've got the D, and what these are SP3 D orbitals. And what I've got is I've got all of them with a single electron in there. And then if I go back with bromine, there was 5 bromines, so they can all pair up. So there's 1, and I could draw 5 more. So the bottom line point here is the hybridization. So I'm going to go over here to the left side of the board here in a second. So when we have the 5 electron domains, any of those, the trigonal bipyramidal or any of those, their shape is going to be trigonal bipyramidal. The axial are 90 degrees. The equatorial is 120 degrees. The hybridization, though, is going to be SP3D. So if I go back over here, then, and so the 5 electron domains, these we can see. Can you guys see me here? So the AB5, the AB4E, the AB3E2, the AB2E3, any of these all of these are going to be SP3D. So to me, from my understanding, if we can determine the electron domains, we then can determine really everything else about the atom. Certainly hybridization. And if you're following me here, you're seeing how the groupings all go together. I mean, we have 4 electron domains. Here's the 3 electron domains. Here's the 2, and now here's the 5. The groupings. Okay, and then the final one is the one that's 6 electron domains, and hopefully the 6 electron domains, hopefully you guys could make a prediction on what is going to happen there. Okay, and also, before I move on, if you look there on the bottom, if I were to diagram the shape, and I'll come back and I'll review that, but I would show in the equatorial, the chlorine on the left, I would shade that in coming towards me, and then the chlorine that's just above it, I would have a dashed line. We'll talk about that more. Okay, so sp3d. Okay, so now on to the octahedral shape. Okay, and again, I'm going to go back and do the same thing I've been doing. Do the dots and count the electron domains. So molecules with an octahedral shape, so the AB6 or octahedral derivative shape, are going to be sp3d2. Okay, and again, I'm going to try and just explain kind of the diagram here. Okay, so if I'm going to do SF6, so again, I'm going to count the valence electrons. So sulfur has 6, and fluorine is 7 times 6 is 42. So I get 48 total dots. I'll put the sulfur in the middle and the fluorines around it. Okay, and then I'll fill the octets. Count. So 8, 16, 24, 32, 40, 48, so everything's good. Count the electron domains, 1, 2, 3, 4, 5, 6. So again, same process. So this is going to be the octahedral shape, and it's going to be nonpolar, bond angles 90 degrees, all that we talked about in chapter 8. But how does this work? Well, fluorine, okay, its last entry is 2p5, which means, again, what we're doing here is we are looking for orbitals that are half-filled. So we've got fluorine, which has got, I'll be consistent here, this goes down. And I got 6 of them. So I got 6 of these singles. Well, sulfur. So sulfur is 1s2, 2s2. So again, I'm going back to electron configurations. So 1s2, 2s2, 2p6, 3s2, 3p4. So if I look at just the outermost level, so here's the 3s. Here's the 3p. And if you think of the dot structure of sulfur, it makes sense. Okay, so pair, and then single and single. But this is one of those expanded octets. This is one of those where now we're in the 3rd row or below. And so what happens here is there's available d orbitals. So here, just like in the one I did in the last one with phosphorus, there's all these d's. So here are the 3 d's. So it's got to be in the 3rd row or below because we got to expand into the d's. And so because it's got 1, 2, 3, 4, 5, 6, it's forming 6 bonds. We're going to promote here and we're going to promote here. So we're going to end up with this. And so these are then going to hybridize again. They're going to cross. They're going to become equivalent. And so what we have is sp3 because there's three p's and then it's d2. So the hybridization here for 6 electron domains is sp3d2. And again, to me, this whole concept of hybridization is what we are doing here is we are explaining the dots. Okay, so then if I go back here and then I complete this table, okay, so where I'm at now is I'm down here on the bottom. So this is the six electron domains. All these are going to be sp3d2. And I don't know about you, but to me, I kind of see that this makes sense. It's kind of cool, but I guess this theory, and I don't know it well enough, but there is some flaws in it, especially when there gets to be odd numbers of valence electrons. And that's something your college professor, if you take it past our class, he or she can explain to you, which I don't really understand that well. Okay, so now what we're going to get into, and I know we don't have too much time left, but I want to get into this a little bit, and then I will come back and, like I said, I'll post a video, and I really think we're going to be close to done with chapter 9. But definitely by Tuesday we'll finish it up and move on. But let me just go to using all our time here. Okay, so we just did that. Okay, and here's a good, and there's a picture like this. I don't know what page. It's in chapter 9. It's a good review, and it shows the hybridization. And to me, the electron domains is really what this is all connected to. Okay, let me just, again, kind of get into this a little bit, is when there's a multiple bond. When there's a multiple bond. So let me just take the next couple minutes on this, and then, again, we might need to revisit this on Tuesday, but I'll explain more on Monday, a video I'll post on Monday. But the hybridization in a multiple bond. So this is when we have a double bond or a triple bond. And what we're going to have here, again, I'm still going to do the same thing. I'm still going to do the dots, and I'm still going to count the electron domains. But for a double bond, there's going to be this thing called an unhybridized P. So it's a P that doesn't hybridize. In a triple bond, there will be 2. And again, I'm kind of rushing through this quickly, but that's simply how I remember it. So C2H4. So if there's a double bond, there's going to be the hybridization. I'm going to do the dot structures, but there will be, in a double bond, there will be 1 unhybridized P. In a triple bond, there will be 2 unhybridized P's. So let me just do this, and this is where we'll stop. Did I share that with you guys? Did you see that? I didn't. My fault. Let me put this up. I didn't do that right. Let me put this up, and then this is where I'll start in. Can you see that now? Kara, Mason, can you see that?
Yeah, we can see it.
So let me just leave this up, and we got like 1 minute, 1 or 2 minutes. This is where I'll start on the lesson I'll post on Monday, and I may need to explain this some to you guys on Tuesday. But in a multiple bond, so I'm talking about a double bond or a triple bond, there's still going to be the same hybridization. We're still going to do the dots. We're still going to count the electron domains, and you'll see this. So you'll see this in the video I'll post on Monday. But when I do C2H4 around the carbons, there's going to be 3 electron domains, which means there's going to be sp2 hybridization. But the extra bond, the double bond, will be what's called an unhybridized P. And so it's a P that did not hybridize. And that's what I will explain again on the video I'll post on Monday. Okay, so I'll post a video on Monday. Things you guys can be working on is the quiz. You can be working on the text problems. You've got the review for chapter 8 and 9. And again, next week, I was telling you we're going to get through 9, and probably Monday or in the early Tuesday we will, and then we're going to move into chapter 10. And I just got to keep moving, try and get us through as much as we can. So, that, any questions you guys have? You know, and Kennedy, I sent you an email too, and if you want to Google Meet later today, just reply back. I'm more than happy to do that. That's true of anybody. If you want to Google Meet with me. If not, guys, I'm done. Have a good weekend. I will post like I said, I'll post a lesson on Monday. We will not Google Meet on Monday. Quizzes due on Wednesday. Any questions you guys have?
No, thank you, Mr. Woods.
Guys, have a good week.
Thank you. Thank you.
Thank you.
You're welcome. And Kara's gone. But anyways, David, I'm going to do that right now.